So, hi everyone, my name is Matúš. I work at STRV as a software engineer, and welcome to the last talk of this evening. We'll continue in the spirit of the performance optimizations, but this time with PGO, which stands for Profile Guided Optimizations. Before moving to the profile part, let me start with the optimizations that are built in to the Go compiler by default. The compiler, in general, is a program that takes your code from one language and translates it to another. While doing this, it performs many optimizations. The most common and the most famous is called inlining. Whenever you call a function from your code, there are a couple of steps that are involved. First, you have to store the values from the registers. You have to create stack for the function. You have to copy the values that are as input parameters. You have to run the function, and everything in the reversed order to return back from the function. It's a very small overhead, but it's still there. Programming language designers and CPU architects work very, very much to optimize this, but they still can take off the overhead that is related to this function call. So you have to consider if this is a problem. Like, this overhead is very small, and when compared to a large function, it's insignificant. But when there is a small, very small function that adds two numbers, do some small calculation, or just some processing in a slice, then the overhead is significant. The only way to eliminate that is inlining. Inlining is very simple. You just take the code from the function that is being called, you copy it, and put it to the caller. Nothing else. It's not something that Go invented. It's present in many other languages. And when you are doing this optimization, you have to think about the size of this overhead compared to the function. When the function is complex, the inlining is not worth it. You just have to take a lot of code and put it in a place which multiplies the size of the code but doesn't bring any significant improvements. And also there are some parts that prevents the inlining at all. The good thing is that it works across the files, across the packages, and the whole code. And this optimization is pretty conservative. So the Go compiler takes a very small, careful evaluations to see if it makes sense to inline any function, because it involves a binary size increase. And to do that, it computes something that is called inlining budget. Go basically runs through the function, it scores every step of it, and if it reaches a certain threshold, the function is not eligible for inlining because it's too complex or too big, and the performance improvement isn't simply worth it. Now let's take a look at a very simple example where we have some add function that just sums two numbers and our function call. When we inline the function, we do exactly what I said. We just take the body of the function and put it to the caller's side. The inlining is usually called the mother of all optimizations because it unlocks the door to other optimizations. In our case, it might be the constant propagation, because Go compiler is smart enough to see that we are just saving two constants, two variables. So it just takes them and puts them where they belong. It can be optimized even further. And now we skip the whole function call to variables allocation. And now we have only our result. As we can see, there is one function that remains unused, which is our add function. And that brings us to another optimization called dead code elimination. Go compiler sees that this is the code that is never executed, so it's being removed from the final binary. And it does not apply only to functions. It applies to all dead branches, all the switch cases that are not being used, basically everything that is not being executed during the run. When Go is working, and when I put it very simply, it works with two types of memory. The first one is stack, that is very close to your code, and it's incredibly fast. And the second one is heap, that takes some overhead related to the memory management. Escape analysis is a technique that runs through your code and checks if any reference to the values in the functions outlives the function. And when this happens, you cannot allocate or you cannot put the variable or the value on the stack. You have to put it on a heap, which includes extra costs to the runtime and cost you some CPU performance and has some memory allocation. When we use our most favorite optimization to inline this function first, we see that we moved the allocation of user from the function new user to our body, which now can be successfully allocated on stack, saving you some CPU time and some memory. The last optimization I would like to introduce is called devirtualization. As we know, one of the strongest features of the Go are the interfaces. So whenever we have some type that has some methods defined over the type, and we have some interface definition, we can use whatever type meets the definition of the interface. The Go doesn't care, it just needs to have the set of functions that are defined within the interface. Now, when you call some function via interface, there is an overhead. The Go needs to go to runtime, it needs to check the jump table, and needs to find the concrete type that implements the function of your interface, and it needs to jump to that implementation. We have a very small example. There is a write function that takes writer interface, writes the data, that's not important. And in our main, we are opening a file. This OS, that file, satisfies the writer interface, so we can pass it to our write data function. First, again, we will use our optimization called inlining, and we take the function and inline it. Now we see that we open the file, we convert it to writer interface, and then it's being used as an interface call. The problem with interfaces and the indirection is that this is a barrier for compiler. The compiler doesn't see behind this barrier and cannot force other optimizations. So that's where the devirtualization kicks in. And when the Go sees that the only type that is ever called, that is ever used to write, is our os.file, it simply removes this indirection and replaces interface call with the direct call to a method. Now, all of these improvements are small and by themselves very insignificant. The important part is that each one of these optimizations unlocks the door and the room for the others. So they stack up, they compound, and together they make a significant improvement that you can see in your programs. When you are optimizing your code, there are a couple of ways. Like in the presentation before, you can collect the profile and optimize the code by yourself. But when you want the compiler to do this work for you, these are the optimizations that are happening in background. And you can tune some of them, but all of them relies only on static analysis. So the compiler sees only your source code and nothing else. So it's very conservative, and it does only what is assured to bring some performance benefits. You might adjust your code to let compiler optimize even further. But the problem is that this will usually result in a disaster. Not only because that these optimizations are specific to the architecture, but also because the compiler optimizations aren't covered by language specification. So they can change in any release, and your effort would be ruined. And you might ask yourselves if there is a way how to support the compiler and making these decisions and optimize it. And you probably know that the PGO is the answer. Now, we know what are the optimizations, and now let's move to the profile part. How to get a profile? There are a few ways how to get them. First one of them is exposing a profiling endpoint. You might see in many examples that you have only a blank import and running some server without anything. Please don't ever do this in production. Not only it exposes the endpoint that is unprotected, but it uses the default multiplexer and the default HTTP server that are not suited for production and shared across the whole program. What I want to demonstrate by this code snippet is that the pprof package exposes the HTTP handler called .profile. You can take this handler and plug it into your router, your multiplexer, and run it on your server, on your HTTP server, which can be authenticated, rate limited, and protected as you wish. Once this endpoint is exposed, what it takes to collect the profile is just simple API call and storing the result as a pprof file or a PGO file. The second way is to collect the profile from the runtime when you just start the collection and end it when you see fit. And there are other options like some cloud tools or continuous profilers that are provided by some other third-party tools. When you have the profile, and I assume that you have the code, now we can put everything together and run. I'm sorry, before that, this is the profile you get out of these collections. If you ever saw this, or this, you are already familiar with that. This is being used for manual optimizations, and it is the same profile that is being used by the profile guided optimization. So we have the profile, and to use it in a compiler build, you just hit go build as you are used to. That's in the case when the profile is named default PGO, or if you want to pass the file explicitly, just use the PGO flag. The good practice is to store this file within the version control system, so your builds are reproducible and everyone can run and achieve the same results. How it works is that it takes these optimizations and it tells the compiler to focus on the hot areas of your code. So these are the ones that are the most popular and the most important for the user. There are two ways how PGO helps the compiler to optimize your code. First is an effort focused on inlining. As I mentioned budget, the inlining budget is pretty small. So when you have a medium-sized function, it's already not eligible for inlining. But when PGO identifies that there is some hot function in your code, the budget increases and it can inline the large functions that are called very often, they are most important performance-wise. The next part is devirtualization. As I mentioned, any indirect call brings extra overhead. So if we take the function from the previous slide that uses writer interface, and if we pass the profile that identifies the most common type that is being used in this function, the compiler can come and can replace the indirect call by the direct call to the types method with a fallback to the interface call. This unlocks the room and the potential for even other and further optimizations by either inlining the method write and so on. Overall, you should gain some performance improvements, but there are some certain small steps that might bring regressions. But each time you run with PGO, the performance should improve. Now, you may ask, why would you do this? And the most important point is the performance. When the Go team ran their benchmark on some pre-selected set of representative Go programs, they realized that there is on average 2 to 14% CPU improvement. And the most important point about this is that you don't need to rewrite your code. And I cannot stress this enough. Like, there are many cases when you hit a wall with the manual optimizations, or when the code base is so large that you are afraid to touch anything, when there is no business approval for you to spend time on optimizations, or if you're just simply afraid to refactor the code because it can bring unnecessary risk, and the result isn't, you cannot be sure that there will be any performance improvement. When you are optimizing your code manually by profiles, you can optimize only your code. But what PGO does, it applies to not only your code, but also to your dependencies and even to the standard library. So it takes every single line of code that is being used, and it gets optimized to yield better performance results. You might not know this, but you are already benefiting from the PGO because the Go team uses this to build the Go itself, which results into faster build times. And the Go team made a promise that they will further optimize the PGO that will bring further optimizations in the future. As we know, there is no feature that comes without trade-offs, and there are some related to the PGO. First one is the profiling overhead. While it's small, there is still some. By some of the tools, it's estimated to be around 5% during the profile, during the profile collection. So it means that it's not a 5% to your CPU all the time. It's addition only during when you are collecting the performance profile. The next overhead is related to the PGO itself. It's the build time. When you are applying PGO, and especially the very first time, the Go needs to rebuild every single line of your code, which will take a lot of extra time. But as soon as this build is cached, it behaves as the regular Go build, which has slightly increased build time. And because of inlining and other optimization, which take the code and copies the code to the places in your code, there is a slight increase to the binary size. There is an obvious downside to this, and that's that you cannot optimize the code that you have just written. You have to first use the code in the production or somewhere. Then you have to collect the performance profile so you know how the new code behaves, and only then it can be optimized. PGO comes with a source stability, which means that when you are linking, or when the Go is linking the profile to the source code, it uses a soft match. So when you are refactoring your code, moving the functions around, or making changes, adding features, there are still a lot of matches. So you still benefit from the PGO, even if there are some code changes that do not relate to the version where you collected the profile from. It also provides iterative stability, which translated is that it might happen that when you collect the profile and you will find a hot part of your code, it will get optimized so much that it will no longer be a hot part or hot path. And theoretically, the next collection of profile would show this initially hot path as a cold one, so it won't be optimized, and then there will be a regression in performance. Go remains still conservative even when using PGO, so this should not happen. And with each iteration, the performance gains should be consistent with the previous versions. And to wrap this up and to get the best of PGO, you should collect the representative data, which means that you are optimizing for your use case, which is usually production. So collect the profiles that are related to your production, that reflect how your users are using your program. If this is not possible, maybe before you are using or building a CLI tool that you cannot profile, or if there is any other blocker, you can use a representative benchmark. Please be very careful with this. It's very hard to get the representative part right. You usually end up with optimizing the part that is not being hot or not being important to your users. If you don't get it right, you don't need to worry, and this might give you some confidence, because whatever profile you use, the PGO should not make your program slower than it was before. And to get it right, you might collect multiple profiles over some periods of time to collect all the specifics of the user behavior, of all the flows that are happening in your program, which then can later be merged to a single profile, combining all the features, all the parts of the day, and used in a PGO build to optimize it the best way possible. The last point from me is a reminder to keep your profiles fresh. As your code base evolves, the profile reflects the older versions of code, so it's great to keep it up to date. And also, as your traffic patterns might change, it's great to refresh them from time to time. Now, what to get from this talk? First, compiler already does some optimizations, but PGO helps the compiler to see. It points out the hot parts of your code, and it lets compiler focus on these important parts. It yields almost free performance improvements, which means that you don't need to touch your code, and it still can be optimized. It's optimizing not only your code, but also your dependencies and the standard library you have no control over, so it brings benefits on all fronts. There is no wrong way to do it. According to Go team, there are only performance gains. You should never see a performance regression, and it's resilient to changes. So you don't need to lock to that version to keep the performance improvements. You can iterate, you can evolve your source code and still benefit from PGO. It's optimizing hot parts of your code, which is also the downside. If you need to optimize some parts that are not hot, you need to do that manually. The PGO has no control over this. The other option is to make a synthetic benchmarks or the synthetic load that will represent all the parts of the code that you want to be optimized. Collect production profiles. It's just simple as getting it right, optimizing for the use case that is most common for you. And lastly, it comes with a very small overhead that is usually worth the improvements. I would like to thank you for your attention, and now is the room for questions.